spans going out from each side. Probably one of the most famous examples is in Scotland, right outside of Edinburgh, the so-called Forth Bridge, F-O-R-T-H. You can see it's supported here with a span running this way and a span running this way, and then the next section is here. Those spans meet up here, and this span goes on this way. But again, basically a beam bridge with triangulation and trusses above and below that ensure that the compression and tension forces are aimed and supported by the columns here in the center. You can see here how those forces actually manifest themselves. You see the compression forces pushing down this way, being supported by the abutments here. Tension forces being resolved this way, and compression here. So all of the weight of whatever is on the roadway here wind up being supported by these pillars. And here is kind of a cross-section of that cantilever bridge. It's a Roman arch bridge. You see what John was talking about before, where these arches are all supporting each other. So the weight moving down on this arch, pushing this way, is counteracted by the weight coming from this arch. And you have a series of these. In this case, I don't know if this was an aqueduct or a viaduct. There's a great example of a bridge like this in northeastern Pennsylvania. It's called it goes by various terms, the Tunkhannock Viaduct or the Nicholson Viaduct, and it's the old railroad bridge. And you come around the curve on the road and it's right there in front of you. It's a fantastic sight. The bridge below here is, everybody recognize this? Everybody recognize this? This is the bridge, I think it is? It's the Sydney Harbor Bridge? Yeah. You can see it's basically an arch with truss work leading to the supports here on each bank. And obviously the big advantage here is you got more room for those boats to get under. Here you can see how the forces work in an arch bridge. Basically compression forces, which in John's example, with the force pushing straight down on top of the arch, the sides of the arch tend to bow out, but in this case, they are held in check by the masonry around it. A couple different examples of arch bridges with the roadway here on top, the arch supporting underneath. We talked about flying buttresses. This was we're about 800 years removed from the advent of flying buttresses. But you can see with the slider, you can see how aluminum reacts to I need 3 hands.
The two labs that you guys have seen, the Forces Lab and the Materials Lab, both of those are PBS.org website flash interactive things, and both of those are posted on the name, right below where you found this, just so you know. They don't work on here because what you're looking at is a PDF. But if you do it through the name and you actually go to the website, it'll work. Oh.
I broke it. This is where Max were involved.
Reinforced, I don't know what's happening now. The one thing is reinforced concrete. This is just concrete edge piece for a yard. And the thing to tell the kids is that concrete, its strength is in compression. And you cannot, if you push down on concrete, you can't do anything with it. It has some tensile strength, but not a lot. It certainly doesn't have bending strength. I don't know if this demo is going to work. I didn't try it at home, so this is an experiment. But, we've got 50 pounds of weights in here. I just want to increase the load. See if it'll, if we're lucky, it's going to play. These are the weights we'll be using on your bridges, basically, if we were to load more on there, this would snap. And what makes reinforced concrete strong is the reinforcing. It depends on reinforcing. When we use concrete bridges, buildings, and you see the first thing they're doing is laying out bars, which, I mean, in Tempe right now, they're building a bridge over Tempe Tank Lake over the top, down, reinforcing bars in the footpath are about 1 inch diameter, which they're making the matting with bending, lacing together before pouring in the concrete. If they didn't have that, there wouldn't be the strength they need in the concrete bed. The steel gives the tensile strength, and the concrete tries to bend. They're trying to stretch those reinforcing rods, and they hold it together. If they weren't there, you couldn't build